So hi everybody and welcome to this 19th video in solutions chapter. So here we'll be discussing about association of solutes in one of the solvents, and so this happens to be the first application of Nernst distribution law. So we want to find out how they are associated. Okay, so let us see. So I have, let me first, okay, so these are your two different phases. This is your phase 1 and this is your phase 2. Okay, let X represent the molecular formula of the solute. Okay, so let me start. Let X represent solute. Okay, so in phase 1, so this is, let its concentration be C1. So this is your X. Concentration be C1. Okay, in phase 2, let X dissociate, let X associate as Xn. Okay, so this X is in equilibrium and these Nx are getting associated as x to the xn. So association is taking place here in one of the phases, that is phase 2, and the total concentration here is C2. Okay, in the first phase it is C1 and in the second phase it is C2. Now what is this equilibrium constant? K dash will be given by concentration of, just a minute. Okay, so what will be the equilibrium constant K dash? So that will be concentration of Xn, okay, and concentration of X to the power n, right? So concentration of products divided by concentration of reactants. Now if I want to find the concentration of X, so this is going to be X K dash, and your concentration of X will be equal to K dash root of n. So I can take this as constant. So n K dash as constant, I can take this as constant into n x n, right? So this is what I have to do. Now at large dilutions, is one assumption that we make. At large dilutions, suppose the solute exists largely as associated molecules. Okay, so which means the concentration of your Xn can be taken as the total concentration C2 in phase 2. Okay, so then your X concentration of X will turn out to be from this equation. Okay, from this equation, concentration of X will turn out to be a constant into C2 root of n. So this is your, I want to call it as A. Now Nernst distribution law, if you go back to the definition and introductory part, you will know that Nernst distribution law is valid only for the concentration of similar molecular species. In the two phases. Okay, that is C1 from A. So what happens from your A, your concentration of X in the down part can be replaced as C1 divided by constant into C2 to the power n, or to the root of n, is equal to constant, and your Nernst distribution law, which was C1 divided by C2 is equal to constant, will remodify as C1 of n, C2 is equal to constant, which I want to call it as Kd. Okay. Now examples include so distribution of benzoic acid and benzoic acid in water and benzene acid, okay, and acetic acid also. In water and benzene. So these are the examples. So these acids exist almost entirely as, these acids exist entirely as dimers, which means they associate. Dimers in what? In benzene, but remain normal in normal state in water. Okay, so why do they stay like that? See, you have a C6H5, right? So this is your benzoic acid. So what happens is benzoic acid undergoes hydrogen bonding in benzene. Just clarify, it is in benzene. So it undergoes, so there is a hydrogen bonding between oxygen and the, okay. So is the case with your acetic acid. So this substance exists in benzene as double molecules, as dimers. So here n was calculated to be 2. So how did we calculate n? Okay. So in fact, how do we know this n is equal to 2? So this comes from our experimental method. What do we know? We know that concentration of Cn divided by C2 to the power n is Kd, right? Now for different concentration terms, this is going to be constant. Distribution coefficient is constant. So we can know this, right? We know this, and therefore this can be calculated for different concentrations because we know this. So that's how n is calculated experimentally. Thank you. See you.